Okay, so now we're moving on to part B of question 1. Okay, so part B here says let the universal set E equals all elements x such that x is less than or equal to 13 and x is a member of natural numbers. Okay, and then we have set A here, which is equals to 1 2 3 4 5. Set B is equals to 4 5 6 7. Set C is equals to 5 6 7 8 9. Set D is equals to all elements x such that x is equals to 2k plus 1 and k is a member of natural numbers. And then we have set G here. Set G here says all elements x such that x is equals to 2k and k is a member of natural numbers. And finally we have set F, and set F is equals to the elements 1 5 9. All right, so part 1 or Roman numeral 1 of part B here says list down the sets U, D, E, given that D and E are subsets of U. So if you pay close attention, there's a mistake here that was made when basically typing out Roman numeral 1 of part B. Why? Because U here is basically being used as the universal set, and we can see that the letter that was used for the universal set in this case was E. So here let's just know that U here is E. Okay, so U is the universal set, and E is definitely the universal set, and then D is just fine, but E here, the E that is being used here is supposed to be set G. Okay, the E here is supposed to be set G, and the E here as well is supposed to be set G. Therefore, it's supposed to read like this: list down the sets E, D, and G, given that D and G are subsets of E. Alright, so this universal or this U here is basically E, to just mean that it is the universal set. So in some questions, U is what's going to be used to represent the universal set, but in this case we can see from what we have here is that E is the one that was used. So to just avoid us being confused, we are going to maintain the letter E. So when we read Roman numeral 1 of part B, it's supposed to read like this: list down the sets E, D, and G, given that D and G are subsets of the set E, or are subsets of the universal set. So let's list down the elements of the universal set of set D and eventually set G. Let's get started. So we are going to start with E here, which just represents the universal set. Alright, and what description have we been given about the universal set in part B? So the description here is all elements x such that x is less than or equal to 13 and x is a member of the set of natural numbers. Therefore, x is a counting number. At the same time, x is less than or equal to 13. Automatically we can see that because we have this inequality here which says less than or equal to, 13 is going to be a part of the set. Alright, 13 has to be a part of the universal set. Alright, and we know that natural numbers start from 1. Therefore, our first element here is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and finally 13. Okay, so this is our universal set. Okay, so we've listed down all the elements in the universal set. Just take note that at the end here we have 13 in case you can't see it properly. Okay, now let's move on to the next set. Let's list down the elements in set D. Okay, and what description have we been given about set D? So the description that we've been given in set D is that all elements x such that x is equals to 2k plus 1 and k is a member of the set of natural numbers. Okay, so what we have here is we have a situation where the element x, which is basically an element in the set D, is equals to 2k plus 1. Okay, and k, the one that is in this equation, is a member of the set of natural numbers. Therefore, in order for us to find what x is, we're going to have to substitute k with the numbers that are in the set of natural numbers. Okay, so let's do just that. All right, so we're going to have x is equals to 2 times 1. Why 1? Because 1 is the first natural number. So we're going to have 2 times 1 plus 1. So 2 times 1 is 2. 2 plus 1 is 3. okay, and x here is now going to be equals to 2 times 2, which is the second natural number, plus 1. And what we're going to have here when we multiply 2 times 2 plus 1 is we're going to get 5. Okay, so 2 times 2 is 4 plus 1, 5. And then we're going to have x is equals to 2 times 3, okay, plus 1, which is going to give us 7. And finally we have x here. X is equals to 2 times 4 plus 1, and this is going to give us 9. And then we are also going to have x is equals to 2 times 5 plus 1, which is going to give us 11. And then x is also going to be equals to 2 times 6 plus 1, and this is going to give us what? 2 times 6 is 12. 12 plus 1 is 13. All right, so we have to end at 13 because in the question here it says that D and the set G are subsets of U. If D and G are subsets of U, or E in this case, that means that the elements that are in D are limited to the elements that are in the universal set. Okay, therefore the elements that are in D have to come from the elements that are in E, and E is the universal set. So because of this condition here, we cannot go further than 13, so we have to end at 13. So now that we are done with finding all our x's, so we're now going to now list down the elements in the set D in an orderly manner. So we're going to have 3 here, we're going to have 5, we're going to have 7, we're going to have 9, 11, and eventually 13. And by doing so, we've basically listed down all the elements in the set D. Now we need to move on and list down all the elements in the set G. Okay, so now let's list down the elements in the set G. Okay, so what description have we been given about the set G? So the description that we've been given here is that G is equals to all elements x such that x is equals to 2k and k is a member of the set of natural numbers, something similar to what we had with the description for set D. All right, so let's find what x is according to the equation, according to the description that we've been given in set G. So x here is equals to 2k, and k is a member of the set of natural numbers, therefore k is a counting number. So in order for us to find x, we are going to have to substitute k for some of the natural numbers, or some of the numbers in the set of natural numbers. So let's do that. So 2 times 1, okay, is going to give us what? Is going to give us 2. And then x is equals to 2 times 2, which is just going to give us 4. And then x is equals to 2 times 3, which is going to give us 6. And then here we're going to have x is equals to 2 times 4, which is going to give us 8. Next we're going to have x is equals to 2 times 5, which is the next natural number, and then this is going to give us 10. And we're also going to have x is equals to 2 times 6, and by doing so we're going to have 12. G is also a subset of E, therefore its elements have to come from the set E, or have to be within the set E. If we're to say x here is equals to 2 times 7, we are going to get 14, and we know that 14 is definitely higher than 13. Therefore this just goes out of the boundary that we've been given, because the condition that we have here is that G is a subset of E. We are only going to end up to 12, so 12 is going to be our last element. So let's list down the elements in the set G in a proper manner. We're going to start with 2, 4, 6, 8, 10, and finally 12. Our set G is equal to 2, 4, 6, 8, 10, 12, and the elements in the set D are 3, 5, 7, 9, 11, 13. So we can see that these elements in set G are odd, and the elements in set G are even. Okay, and then we also have listed down all the elements in the set E. Therefore we are basically done with Roman numeral 1 of part B. So now we can move on to the next question. So now that we've listed down all the elements in set E, set D, and set G, we can now move on to Roman numeral 2 here. So if we pay careful attention, after being taught to list down the elements of the sets E, D, and G, we had been taught down here at the end of Roman numeral 1 of part B that hence find the following sets. Okay, so now let's start with Roman numeral 2 here, where we have A intersection C union G complement. Okay, so this is what we are being told to find now that we've listed down the sets E, D, and G. So now let's get started. So when we look at this set here, A intersection C union G, we know what set A is, we know what set C is, we know what set G is, but what we do not know is set G complement. So let's list down set G complement. We can see that set G here has 2, 4, 6, 8, 10, 12. So which elements are not in this set? We can see that 1 is not a part of set G, so 1 is definitely going to come into G complement. 2 is a part of set G, therefore it cannot be here. But 3 is not a part of set G, therefore it has to be a part of G complement. We can also see that 5 is not a part of G, therefore it comes into G complement. 7 also comes into G complement. 9 also comes into G complement. 11 also comes into G complement, as well as 13 is a member of G complement. G complement is equals to 1, 3, 5, 7, 9, 11, and 13. Okay, so we know what G complement is. Now we need to find what C union G complement is. So this just means that we need to combine all the elements in G complement and all the elements that are in set C. Alright, all these elements that are in set C, where we have 5, 6, 7, 8, 9, we need to combine these elements with all the elements in G complement. Let's do that. We're going to start with 1 here from G complement, and then we're going to have 3 from G complement. We are then going to have 5, which is both in G complement and C. Okay, and then we're going to have 6, which is in C, and then we're going to have 7, which is in both C and G complement. And then we're going to have 8, which is just in C, and then we're going to have 9, which is in both set C and G complement, and then we're going to have 11 and 13, and these two elements, or these two last elements, are coming from G complement. Therefore C union G complement is equals to 1, 3, 5, 6, 7, 8, 9, 11, 13. So we've listed down all the elements in C union G complement. Now that we have found C union G complement, let us find A intersection C union G complement. Let's do just that. So now what we're being asked here is to find what is common in the set A and the set C union G complement, and we've already found what C union G complement here. This is the set, right? And we know that A right here is equals to 1, 2, 3, 4, 5. So now let's find what's common in the set A right here and the set C union G complement. So what's common? If we look at A has 1, C union G complement also has 1, so 1 is common. A has 2. Does C union G complement have 2? No, it doesn't. So 2 is not going to be a part. 3, A has 3 here, and so does 3 C union G complement. So we're going to have our 3 there as our next element. A has 4. Does C union G complement have 4? No, so 4 is not going to be a part because it's not common. But A has 5, and also C union G complement also has 5. So, and the fact that 5 is the last element in set A, we are going to end this set right here at 5. So we've basically found Roman numeral 2 of part B. Okay, now let's move on to Roman numeral 3 of part B. On question 1, we're basically being told to find A minus B. Now when we look at A minus B is just the same as saying A intersection B complement. This is just the same as that. So when we see this and we see that, they're equally the same. Therefore the elements that are in here and the elements that are in there are exactly the same, because these two sets are basically one and the same set. Okay, so we've just rewritten A minus B in such a way that it is now A intersection B complement. So converting A minus B to A intersection B complement makes it easier for us to basically find what A minus B is, as compared to where we just have a situation where we say A minus B. It's confusing like that. But now, before we can actually go any further, I think it'll be only beneficial for us to like try and prove why A minus B is equals to A intersection B complement. So let's take for instance, if our set A, right, we're just going to use imaginary elements. In this case, we're just making this up because we're trying to prove that definitely A minus B is equals to A intersection B complement. So let's take for instance, if A, set A was equals to the elements 1, 2, 3, and 4, okay, and then set B was equals to the elements 3, 4, 5, and 6. Okay, so this is set B. So now if we start with the left hand side here, right, so let's start with the left hand side where we have A minus B. A minus B just means that from the set A, remove all the elements that are in B. Okay, so A minus B just means from the set A, remove all the elements that are in set B. So when we look at A here, A is 1, 2, 3, 4, and B is equals to 3, 4, 5, 6. And based of our description of what A minus B is, we have to remove from A all the elements that are in B. So when we look at set A, which elements are also in set B? So we can see that the elements that are also in set B in set A are 3 and 4. Okay, therefore A minus B is going to be equals to 1 and 2. Alright, because we've basically subtracted from A all the elements that are in B. So we've subtracted B from A, therefore we've removed all the elements that are in B from the set A. And when we do that, we remain with 1 and 2. Now let's deal with the right hand side in this case. Okay, so the right hand side is this side where we have A intersection B complement. Let's find what B complement is. We know what B is here. So set B is equals to 3, 4, 5, 6. Alright, so set B is equals to 3, 4, 5, 6. Now we need to find B complement, which is just a set of all the elements that are not in B. So when we look at the two sets here, we know that 1 is not in B, as well as 2 is not in B. So B complement is what? Is equals to 1, 2. Okay, fine. Alright, and now let us now look at what's common between the set B complement and set A. Alright, so what's common between B complement and the set A? Because on the right hand side here, remember that we have A intersection B complement. So what's common between the set A and the set B? So when we look at the set A has 1 here, so does B complement, it also has 1. Set A has 2 here, and B complement also has 2. Therefore, A intersection B complement is going to equal 1 and 2. And if we look at A intersection B complement and A minus B, we can see that we have the exact same answer. Therefore, we have proved that A minus B is the same as A intersection B complement. Now we've proved that A minus B is equals to A intersection B complement. Let's now find A minus B. But in order to find A minus B, we're going to use A intersection B complement, because like we said earlier, converting A minus B to A intersection B complement is way much easier for us to actually find A minus B. Okay, so we're going to have A here intersection B complement is equals to, so this is where we're going to list down now the elements in A intersection B complement. So now let's look at A here. A we have 1, 2, 3, 4, 5, and B we have 4, 5, 6, 7. What we do not know at this point is what B complement is. We know what A is, we know what set B is, but we do not know what B complement is. So let's find B complement. So B complement is just a set of all the elements that are not in the set B. And here when we look at the question here, B is equals to 4, 5, 6, 7. So we know that in B complement we are going to have 1, 2, 3, 4 is a part, 5 is a part of set B, 6 is a part of set B, and 7 is a part of set B as well. Therefore, the next element that is part of B complement is going to be 8, 9, 10, 11, 12, and 13. Alright, so this is our B complement. So now let's find the intersection between A and B complement. What's common between this set and the set A right here? Okay, so B complement has 1, the set A also has 1, so we're going to have 1 there. B complement has 2, so does the set A. Alright, so we're going to write 2 there. B complement has 3, but so does A as well. So 3 is also common in both sets, so we're going to write down 3 there. And 8, no, is not common in both sets. 9, 10, 11, all these are not common. Therefore, our A intersection B complement is going to be 1, 2, 3, meaning that our A minus B is equals to 1, 2, 3, because A intersection B complement is just the same as A minus B. So our next question is Roman numeral 4 of part B, and here we are being required to find the set A intersection B minus C. It's going to be difficult for us to find this set in this form, so we're going to have to simplify it. Okay, so if we simplify it, we're going to now have a situation where we have A intersection B intersection C complement. Okay, so this is what we're going to have. So when we convert this negative sign to intersection, our C here is also now going to get a complement symbol right there on its power. So we've basically converted this guy to this guy, and this is the guy we are going to use to find our set A intersection B minus C. Alright, so here we're going to write down A intersection B intersection C complement is equals to that. So we're going to list down our elements right here. So we know what our set A is individually, we know what our set B is, we know what our set C is, but what we do not know is what our A intersection B is, and what we also do not know is what our C complement is. Okay, so let's start with C complement. So C complement is just a set of all the elements that are not in the set C, and if we look here, our C is equals to 5, 6, 7, 8, 9. Therefore, the elements that are part of C complement are going to be 1, 2, 3, 4, 5, 6, 7, 8, 9 are a part of C, so we're not going to include them in the set C complement, and therefore the next elements that are in C complement are going to be 10, 11, 12, and 13. Okay, so this is our C complement. Great. And now we're going to also have to find what our A intersection B is. Okay, what's common between the set A and the set B? So when you look at set A, we have 1 there. Do we have 1 in set B? No. We have 2 in the set A. Do we have 2 there? No. We have 3 in the set A. Do we have 3 in the set B? No, we don't. But we have 4 in set A, and we also have 4 in set B. We also have 5 in set A. We also have 5 in set B. Therefore, the common elements in both set A and set B are 4 and 5. Alright, so that's our A intersection B. Now we know what our A intersection B is. We also know what our C complement is. Let us find the set A intersection B intersection C complement. So when we look at both sets, the only element that's common in C complement and A intersection B is what? Is 4. Therefore, A intersection B intersection C complement is going to equal 4. Alright, and this is our final answer. So the next question that we're going to be working on now is Roman numeral 5 of part B, which is denoted by the letter V, as we can see. And on this question, we're being asked to find F minus A intersection D complement. Alright, we're being asked to find F minus A intersection D complement. So this is what we have to find, but in order to do that, we need to simplify this, because in this form it's going to be difficult for us to do so. And when we simplify it, we're going to have F intersection A intersection D complement complement. If we simplify this further, we're going to have F intersection A intersection D, and the complements cancel out each other. Therefore, there will be nothing here. There will be no complement anymore. Therefore, the only thing that now we need to find is F intersection A intersection D. So we already know what our set F is. We already know what our individual set A is and our set D. But now what we want to find is our A intersection D. So our A intersection D is basically what's common between the set A and the set D. Alright, so in our set A we have 1 here, and in our set D here, which we have over here, we have no 1. Okay, in set A we have 2, set D over here we have no 2, but we have 3 in set A. We also have 3 in set D, so we're going to write 3 there. What else do we have? 5 is actually common in both sets, so 5 is there. That means that our A intersection B is going to be 3 and 5. Now that we have that out of the way, let's find what's common between the set F and the set A intersection D, which is what we are from finding. So what's common between the set F and the set A intersection D? Okay, so when we look at our set F, we have 1, we have 5, and we have 9. And in our A intersection D, we have 3 and 5. So automatically there we can see that the common element there is simply just 5. So 5 is the element that is common in the set F and the set A intersection D. And by doing so, we've actually found the set F minus A intersection D complement. The answer is 5. And we are done completely with part B of question 1, which means that now we can move on to part C of question 1. Can you be mine? Try to walk on a queen.